This is the ninth lecture of digital signal processing. Last time we have started this transformation, and I have shown you how to do this transformation. Right? So what is left for today is the inverse Z transformation and the transfer function. So therefore, first of all, we'll take a look at the inverse Z transform. So as I have told you, you have learned a Laplace transform. In Laplace transform, you have Laplace transform, then inverse Laplace transform. So likewise, in Z transform, you will have Z transform and inverse Z transform. So in Z transform, you will transform xn to xz. Right? That means from time domain to Z domain. And in inverse Z transform, what you are going to do is you will transform from xz to xn, which is from Z domain to time domain. So before going into Z inverse Z transform, first we'll take a look at this table that I have given you previously. So if you take sequence and Z transform, delta n Z transform is equal to 1. That means inverse Z transform of 1 is equal to delta n. Okay, in first row. Okay, then you have a to the power n un, right? And the Z transform of that for the region of convergence, magnitude of Z larger than magnitude of A is equal to 1 over 1 minus A Z minus 1, right? So the inverse Z transform of 1 over 1 minus A Z minus 1 is An into Un. Okay, so likewise these are actually Z transform pairs. That means from sequence you can get the Z transform, and from Z transform you can see what is the inverse Z transform as the sequence. Okay, so delta n Z transform is 1, inverse Z transform of 1 is equal to delta n. So likewise for all the other cases with the region of convergence, what you are seeing here is the Z transform pairs. So therefore we will use these transform pairs. So these things are previously found values, found things, right? So as you can remember, we have proven few of these things, right? So therefore when you are doing the Z transform or the inverse Z transform, you are not going to prove that again and again. Basically what we can do is we can use what we have written here. Means these tables can be used when you are finding Z transform or inverse Z transform, right? So here this is at top of the page, you can see xn equal 1 over 2πg integration xz zn minus 1 dz. So this is the inverse Z transform equation. So when you know xz, you can find xn. But remember, we rarely use this equation in order to find the inverse Z transform. Most of the time we will use the other few methods that I am going to teach you today in order to find inverse Z transform. Because this equation is somewhat complex, and there are easier methods than this in order to find the Z transform. For your knowledge, I am giving you this equation, but we are not going to use this frequently in order to find the inverse Z transform. This equation we are not going to use. right? So first of all, we'll take a look at our method of finding this inverse Z transform, inspection method, right? So you can find the inverse Z transform from Z transform pair the table, right? So I have shown you that table previously. So here in this example, what we have is xz. Xz is given as 1 over 1 minus 1 over 2 z minus 1. Okay, that is xz. So you can see xz in this example and the region of convergence as well. Magnitude of result, it is larger than 1 over 2. So this region of convergence is actually, if you draw a circle in z plane which has a radius of 1 over 2, so the region of convergence will be outer to the circle that you are drawing. Okay, so that's what it means. So therefore, if you can remember, in the table you have seen, when you have a n u n, the z transform is equal to 1 over 1 minus a z minus 1, right? As it is shown in here. Z transform of a n u n is equal to 1 over 1 minus a z minus 1 for the region of convergence magnitude of z larger than a, right? So remember, when this region of convergence changes, uh, the xn, which is the time domain or the sequence, will change. So therefore, always you have to refer region of convergence as well when you are trying to find the inverse Z transform. So Z transform of a n u n is equal to 1 over 1 minus a z minus 1. That means inverse Z transform of 1 over 1 minus a z minus 1 is equal to a n u n for the region of convergence when we have z magnitude of z larger than a, right? So therefore if we compare this thing with our xz, so our xz is 1 over 1 minus 1 over 2 z minus 1. So if you compare these two, value of a is actually 1 over 2, right? So therefore our xn is, the xn for this example is actually 1 over 2 to the power 1 over 2 and to the power n un, right? So what we have done here is just the comparison. So this is, therefore this is called the inspection method. So previously we have results that has obtained previously. So from that previous results we are finding the inverse Z transform like this. So therefore this is called the inspection method of finding the inverse Z transform. So that table, right? So if you can remember, we have proven some of those things, but in here you don't have to prove. You can use the results that we have previously obtained directly in order to solve this. Means in order to find xn, you can directly use this thing. So here we are doing the comparison. Actually comparison means it is called an inspection. So this is the inspection method of finding the inverse Z transform. This is the other method, right? This method is called partial fraction expansion, right? So partial fraction means, so if you have any fraction means most of the fractions, right? Fractions, you can express that fraction as an addition of whole number plus few partial fractions, right? So again, fraction or the rational fraction, we can express that as an addition of partial fractions with a with an integer value, right? So when you have that fraction, what you have to do is what you can do is you can expand that thing. Expand it means expressing it as an addition of partial fractions and an integer value, right? So this shows you a theoretical example, right? When you have xz as it mentioned like this, right? As it mentioned like this, then you can find the partial fractions of xz as given in below, right? Xz, that will be equal to sigma r equals 0, m minus n, b r z minus r plus sigma k equal 1, and the k, then k not equal to I n. So likewise the u will have very large, very somewhat complex partial fraction expansion term expression in here, right? This looks somewhat complex because we don't have the actual values. We are using some symbols in order to find this partial fraction expansion in here, right? But it will be very much simple if you are going to find this in with the actual values, right? So therefore we'll see an example of doing this finding inverse Z transform using this partial fraction expansion, right? So first of all, what we have to do is, in here this is just what I have shown in here is just how to find the partial fraction. I haven't shown you how to find the inverse Z transform. So remember, first of all, our task is to find the partial fraction expansion. Afterwards, I'll tell you how to find the inverse Z transform. Consider when you were given xz like this. So xz equal 1 plus 2z minus 1 plus z minus 2 divided by 1 minus 3 over 2 z to the power minus 1 plus 1 over 2 z to the power minus 2, right? So in here, what is the numerator? The numerator is the upper value of the fraction. That means 1 plus 2z minus 1 plus z minus 2, right? So what is the denominator? Denominator is 1 minus 3 over 2 z minus 1 plus 1 over 2 z minus 2, right? So therefore what you have in here is, this is a rational fraction with actual values, right? So here this looks somewhat complicated because it contains z minus 1 terms, right? But actually xz is this. Xz is actually z squared plus 2z plus 1 divided by z squared minus 3 over 2z plus half. So this is actually xz, right? But in here in our question we were given it like this, right? So same xz as expressed in a different way, right? So in here actually it is expressed in z minus 1 terms. That's because, if you can remember, when you have z transform, what you have is like z minus 1, z squared, z minus 2, z minus 3. So likewise, like z to the power terms, most of them are like negative terms. So if you can recall the Z transform, not inverse Z transform, Z transform equation, that will consist of Z to the power minus n terms, right? So therefore that's why they have Z minus 1 terms in here, right? But actually the xz in here is z squared plus 2z plus 1 divided by z squared minus 3 over 2z plus 1 over 2. So you numerator and denominator, since this is a fraction, we can express this as in different ways, right? So this is how it has expressed in here. Okay, so same thing, right? Same xz is given here, right? So same xz is this. Okay, so therefore in this xz we can write like 1 plus z minus 1 squared divided by 1 minus 1 over 2 z minus 1 into 1 minus z to the power minus 1, right? So like this. So you may think how I have found factors in here, right? So what you have to do is how I have found fractions or factors like this in this form. So what I have done is actually I have considered xz, which is given like z squared plus 2z plus 1, like z to the power terms, not z minus 1 terms, right? The thing that you can see in here, squared plus 2z plus 1 divided by z squared minus 3 over 2z plus half, right? So I have found factors in here, right? That is actually z plus 1 squared. So numerator 1 squared, right? Denominator z minus half into z minus 1. So just then what I have done is I have divided both numerator and denominator by z squared. Then you are getting x is equal as 1 plus z minus 1 squared, 1 minus 1 minus half z minus 1, 1 minus z minus 1. So then what you can see it in here is if you refer xz, right? Uh, in the numerator it has a maximum power of z as 2, right? And the denominator also it has maximum power of 2, right? So remember, we are still in the process of finding partial fractions, right? So not finding the inverse z transform, we are in the process of finding partial fractions, right? So when we have same same the numerator and denominator, right? Numerator and denominator, what we can conclude is, in order to find partial fractions is, so there will be partial fractions like this. B naught is some kind of integer, not integer, it will be some value, right? So B naught will be some value, right? It will be some value, B naught plus real value, right? B naught, let's say real value, then plus B naught plus A1 divided by 1 minus 1 over 2 z minus 1 plus A2 1 minus z minus 1, right? So that's what it says. So can you see these two factors, like 1 minus 1 over 2 into z to the power minus 1, that is one factor of the denominator. So it will have a numerator of a1, right? Plus then a2 is the numerator of 1 minus z minus z to the power minus 1 factor, right? So like this you will have partial fractions. You can expand partial fractions like this. Xz will be b naught will be some kind of value, and this value means it will not have z terms or z minus 1 terms, plus a1 divided by 1 minus 1 over 2 z minus 1 plus a2 divided by 1 minus z minus 1, right? So what you are seeing in here is the partial fraction expansion of xz, right? So if we know a1, a2 and b naught, right, these three values, we can directly find inverse z transform, right? But here, but in here, right, we don't know B0, A1, A2 values. So our next task is finding A1, A2 and B0. Okay, so uh, still we are in the process of finding partial fractions, right? So we haven't got into finding finding inverse the term. So we are still in the process of finding partial fractions. So how can we find B naught? Right? So in order to find B naught, what you have to do is you have to divide. You have to divide uh, numerator of xz by denominator of xz. Right? So in here, what we can use is long division. So B naught can be found by long division. So in here, right? So can you see this long division? I am dividing z to the power minus 2 plus 2z minus 1 plus 1, which is the, what is this? This is the numerator of xz. And I am dividing it by denominator of xz, which is 1 over 2z minus 2 plus, so minus 3 over 2 z to the power minus 1 plus 1, right? So how can we divide this, right? So I have shown you this division. So it is like this, right? So first consider 1 over 2 z minus 2, right? So how many of 1 over 2 z minus 2 to the term z minus 2? Okay? They are actually 2 of 1 over 2 z minus 2 to the z minus 2 term, that you can see it in the numerator. So it is actually 2, right? So therefore in here what we are doing is we are trying to cancel out our z to the power minus 2 term in the numerator, right? So think like that. So twice, right? So 2 in, then what we are doing is we are multiplying 2 with the denominator. So when we multiply 2 with each value of the denominator, what we are getting is z minus 2 minus 3 z minus z 3 z to the power minus 1 plus 2, right? So like that. Then what you are doing is you will subtract that thing from your numerator, right? Then you are getting is 5 z minus 1 minus 1, right? Okay, you can see it in here. So value of B naught is actually what? Value of B naught is 2, right? So xz, right? Xz, we can actually write it as 2 plus uh, minus 1 plus 5z minus 1, which is the remainder that we got from the long division, right? And with that 2 factors, right? So the same thing that we have in here, right? Same thing, right? So we have found our B naught value. So next task is to find in A1 and A2, right? Here we need to find A1 and A2. This equation. So what you have to do is, let's say you ask to find A1, right? If you ask to find A1, what you are doing is you have to multiply the xz by you have to multiply xz by 1 minus 1 over 2 z minus 1. Can you understand? So in order to find A1, right? A1 is the numerator of 1 minus 1 over 2 z minus 1. Okay, A1 is the numerator of 1 minus 1 over 2 z minus 1 factor. So therefore, what you have to do is you have to multiply xz by 1 minus 1 over 2 z minus 1. Then what you are getting? Then what you are getting is 1 plus 2z minus 1 plus z minus 2 divided by 1 minus z minus 1, right? So because 1 minus 1 over 2z minus 1 will cancel out, right? So in order to do this you have to write down from the beginning, right? So you can refer what is xz. Xz is 1 plus z to the power minus 1 and the whole is squared divided by 1 minus 1 over 2 z to the power minus 1 into 1 minus z to the power minus 1. So when you multiply it with 1 minus 1 over 2z to the power minus 1, what is left will be 1 plus 2z minus 1 plus z minus 2 divided by 1 minus z to the power minus 1. Right? Then what you have to substitute is z to the power minus 1 equal 2. Right? So what is this z to the power minus 1 equal to? So that value you are getting when you equate 1 minus 1 over 2 z to the power minus 1 to 0. Right? If you equate 1 minus 1 over 2 z to the power minus 1 to 0, what you are getting is z to the power minus 1 equal 2. Right? So that value you substitute to this xz multiplied by 1 minus 1 over 2 z to the power minus 1, which value that the value that you have got in here, right? So then substituting by z to the power minus 1 equal to, what you are getting is a1 as minus 9, right? So likewise, how can you find a2 then? In order to find a2, right, what you have to do is you have to multiply the xz by 1 minus z to the power minus 1, because a2 is the term or a2 is the numerator of 1 minus z to the power minus 1 factor, right? So then what you are getting is 1 plus 2z to the power minus 1 plus z to the power minus 2 divided by 1 minus 1 over 2 z to the power minus 1, right? And for that one, substitute back z to the power minus 1 equal 1, right? So like this. So z to the power minus 1 equal 1 is, you are substituting that one because equate 1 minus z to the power minus 1 to 0, then you are getting is z to the power minus 1 equal 1. So therefore when you substitute it z to the power minus 1 equal 1 to this, you are getting a2 is equal to 8, right? So likewise we have found now b0, a1 and a2, right? So finding a1 and a2 it is not that tricky, right? If you understand, you can see. So compare with the equation I have given, ak equal 1 minus dk z to the power minus 1 multiply by xz and substitute z equal dk, right? So ak means the value that you are getting, the value you are getting for 1 minus dk z minus 1 factor, right? So same as a1 and a2, right? 2 minus 9 over a1 is minus 9, therefore minus 9 over this thing plus 8 over 1 minus is to the power minus 1, right? So this is where we have completely found our partial fractions. So still we haven't found the inverse z transform. What we have found is just the partial fractions of xz, right? So repeat this question one few times, right? If you can, in order to get good understanding, right? So now we go to next step, finding the inverse z transform. So before that, right, what we have is in xz. So if you have written xz, you can see xz is 2 minus 9 over 1 minus 1 over 2 z to the power minus 1 plus 8 over 1 minus z to the power minus 1, and you are asked to find this for ROC magnitude of z larger than 1, right? So therefore we have actually 3 terms, right? So xz is in xz we have 3 terms: 2 minus 9 over 1 minus 1 over 2 z to the power minus 1, 8 over 1 minus z to the power minus 1, 3 terms, right? So in order to find inverse Z transform, we are going to find inverse Z transform by taking each, right? So let's take term 2, right? 2. So what is the inverse of 2? So inverse of 1 is delta n, therefore inverse of 2 is 2 delta n. And region of convergence is all Z, therefore not to worry, right? Then next part, minus 9 over 1 minus 1 over 2 Z minus Z to the power minus 1. So that term is, it is like 1 divided by 1 minus a into Z to the power minus 1. So the inverse Z transform will be a n u n, right? So instead of a, what we have is 1 over 2, right? So since it is multiplied by minus 9, the inverse Z transform will be minus 9 into 1 over 2 to the power n un, right? So you can see it in here. We have another in the table. In the table, you can see we have another inverse Z transform for the same 1 over 1 minus a into Z to the power minus 1, right? Which is when ROC, or region of convergence of, is magnitude of Z less than a, right? But we are not going to take that, because what we need is magnitude of Z larger than a, right? Larger than a means that region of convergence is the thing that we need, right? So for minus 9 over 1 minus 1 over 2 Z minus 1, we can write inverse Z transform a to the power n, that means 1 over 2 to the power n un multiplied by minus 9 with the region of convergence magnitude of Z larger than 1 over 2, right? For that one, 1 over 2. So that's correct. Then for next one, which is 8 over 1 minus Z to the power minus 1. Again, same thing. Again, the same thing that you will have. You can find inverse of that as a n u n. A is actually 1. So 1 to the power n, which is 1 into un, and it is multiplied by plus 8. So 8 un, right? And the region of convergence will be magnitude of Z larger than 1, right? So um, therefore in our question we were asked to find xz. Xz is given region of convergence magnitude of Z larger than 1. Therefore if we take first term, which is 2, region of convergence is all Z, right? Then if we take the next term, minus 9 over 1 minus 1 over 2 Z to the power minus 1, region of convergence is magnitude of Z larger than half, right? So larger than half, we can go it for Z larger than 1. Therefore that will be the Z transform, inverse Z transform of that one will be minus 9 into 1 over 2 to the power n un, right? Then consider xz term 8 over 1 minus Z to the power minus 1. So region of convergence of Z, magnitude of Z larger than 1, we can write it as 8 into 1 to the power n un, which is 8 un. So therefore we have found our xn like this, right? So what we have done is we have checked the ROC, right, and we have used this table in order to compare with our answers. So that means we are using the inspection method again. So therefore what we have is xn as 2 delta n minus 9 into 1 over 2 to the power n un plus 8 un, right? So this one, what you can do is you can practice this thing again by drawing the region of convergence, right? So in order to write xn like this, every region of convergence should be satisfied, right? Otherwise we cannot write it, because there are actually two methods of finding the finding the sequence for the same Z transform, as you can see it in the table, right? So therefore, draw the region of convergence and find the inverse Z transform by 1 by 1, right? That means by find the inverse transform of the first term, then the second term, then third term, then add them together by considering the ROC, right? Then you can find the final xn value. Okay. So then we have another method of finding inverse Z transform, power series expansion, right? So this is very much a simple method of finding the inverse transform, right? So here, so if you remember, right, in Z transform, right, Z transform is in this form, right? Xz is equal to sigma n is from minus infinity to plus infinity, xn is to the power minus n, right? And if we expand, what you can see is here, I have shown you only few terms in here, right? What you will see is x minus 2 is a squared, right? So that is when n is equal to minus 2 plus x minus 1 is to the power 1, that is when n is equal to 1. X0 is to the power minus 0, that is when n is equal to 0. Then x1 is to the power minus 1, when that is when n is equal to 1, plus x2 is to the power minus 2, that is when n is equal to 2, right? So can you see this pattern, right? That means let's say in xz, let's say you were given xz. In xz, if you were given xz, then let's say it is not a fraction, it will be consider it is like something like this, then z squared, right? Let's say there's a term called 2z squared, right? 2z squared, let's say 2 multiplied by z squared. So that means that is the term when n is equal to 2, right? Can you understand? N is equal to minus 2. N is equal to minus 2, right? Let's say you will have a term like 3 is to the power minus 1. 3 is to the power minus 1. So that term, right? So that term is the term when n is equal to 1. Can you understand? So likewise, so we'll see an example. Okay. So here xn can be found by identifying the coefficients of the appropriate power of z to the power minus 1, right? So here you can see in this one is let's see in this xz you can see x1 is to the power minus 1. So x1 is to the power minus 1, that is correspond to from z to the power minus 1, you can see z to the power minus 1, the power is n equal 1. That means x1 that is the value of x when n equal to 1, right? So likewise, so we'll see this example. So this is what you got, right? xz is given like this, many terms, right? So what you are asked to find xn, that means you are asked to find the inverse uh, Z transform. So how to find inverse Z transform is, first of all, what you can do is you can expand this thing, right? Expand means remove all the brackets, right? So remove all the brackets, then you get something like this, right? Z squared minus 1 over 2 Z minus 1 plus 1 over 2 Z to the power minus 1, right? So after you got this, what you can say, so Z squared, right? So let's see xz, the expanded one xz, you will have z squared, that thing is corresponding to n equal minus 2, right? So this is z to the power minus 2, which is z squared, right? So that term is is for n equal minus 2 term, right? Then minus 1 over 2 into z, right? So 1 over z power 1, right? Z to the power 1 is actually, if you are writing it like that, we can write it as z to the power 1, that is equal to z to the power minus 1. That means when n is equal to minus 1, so when n is equal to minus 1, the xn value is actually this minus half. Can you see? Then the next term, minus 1 is z to the power 0. Minus 1 is minus 1 to the power z to the power 0. That means that minus 1 is the value when n is equal to 0, right? Plus 1 over 2, 1 over 2 is z to the power minus 1. So z to the power minus 1 means that is when n is equal to plus 1. Right? Z to the power minus 1 you are getting when n is equal to plus 1. That means 1 over 2 is the value of xn when n is equal to 1. Right? So we'll see it like this. Xn equal. So likewise we can write. Okay. So we have expressed xn like this. Right? So by inspection, right? Inspection means not using that method, by inspecting this with our actual expansion or the expansion of our actual Z transform, right? So this is not the way represent in Xn, right? We can represent Xn using uh, an expression like this, right? So using weights and unit sample, we can write down Xn as 1 delta n plus 2 minus 1 over 2 delta n plus 1 minus 1 delta n plus 1 over 2 delta n minus 1, right? So delta n plus 2 will represent when n is equal to minus 2, delta n plus 1 will represent n equal plus 1 value, right? Delta n will represent n equal 0 value, delta n minus 1 represent n equal plus 1 value, right? So likewise we have found our xn value, which is the inverse z transform. Okay. We have finished inverse z transform, right? So then we'll move on to transfer function, right? So here these things, right? When xn is the input and yn is the output, you can write yn convolution with xn, right? So hn is the impulse response of the system, right? Impulse response of the system, right? If we express this relationship in z domain, right, it will be like this, right? So as I have previously told you, uh, convolution will convert it to multiplication, so therefore it will equal hz multiplied by xz, right? So therefore hz is equal to yz divided by xz, right? So yz is the z transform of output divided by xz is a transform of the input. if we are writing xz in terms of hn, actually xz is the z transform of hn, right? Here, the LTI system can be described by means of a constant coefficient linear difference equation as follows. So I have shown yn can be written like this, right? Xn minus k will represent the past input values, and yn minus k will represent past output values. So that will consist of. Then if we convert this one to z domain, you will get something like this. So then what we can do in here is after getting yz like previously, what you can do is you can take yz terms to one side and xz terms to the other side, then divide xz yz by xz, you will get this hz, right? Like this, right? So no need to worry about these things that much. These are just some given symbolic representation. So we'll see some actual representations or actual examples of this thing. Okay. Here, determine the transfer function and the impulse response of the yn is given. Yn is equal to 1 over 2 into yn minus 1 plus 2xn. Right. So how can we obtain the transfer function of this? Right. So what you have to do is you is a transform of the total equation. Transform you get is yz is equal 1 over 2 multiplied by z to the power minus 1, right? Because yn minus 1 will have z transform of z to the power minus 1 into yz, right? And plus 2 into z transform of xn is xz, right? Like this. Then what you can do is you can take all the x values to one side, then y values to the other side, then divide yz by xz. Then you are getting transfer function hz like this. 2 divided by 1 minus 1 over 2 into z to the power minus 1, right? So likewise we have found hz. Right. So why we are finding this hz is, from this one we can tell a lot of things about the system, right? So hz is representing the system. The system means the input output relationship, right? So if you take the inverse, right, so you can find the inverse like this: 2 into 1 out of the power n un, right? So again, using the inspection method, directly we can find h. Okay. Here we can consider this example, right? So consider this example, hz, it is equal to z divided by z minus 0.7, right? So then that is actually 1 over 1 minus 0.7 into z to the power minus 1, right? So we can represent hz, right? We can represent hz in the z plane, right? Hz means actually what we are representing is the zeros and poles of hz, right? So what is meant by a zero is zero is a value where the numerator becomes 0. So in hz equal z divided by z minus 0.7, numerator is z. So z is becoming 0 and z is equal to 0, right? Then it is marked by a 0, that is called a 0. Therefore it is marked by a circle in the z plane, right? Then denominator is z minus 0.7, right? So therefore when z is equal to 0.7, denominator becomes 0. So that part we are calling it as the pole. So pole is marked by a cross in the Z plane. So as you can see in here, right? So in this blue color, right? So these things are the Hn value, right? Hn is 0.7 to the power n un. If you find the inverse of Hz, you can find Hn, right? So Hn will be like that, and it has drawn as well. So what we can tell about Hn is that is the causal system, or it is the right hand side system, Hn. Here, this is actually just my representation. What I have done here is I have represented magnitude of Hz as a in a 3D form, right? So you can see the real and imaginary z-axis, right? So let's say the real axis is like the x-axis, right? Imaginary axis is like the y-axis, and hz is the perpendicular z-axis, right? So perpendicular axis, right? So you can use MATLAB in order to draw this. So this is what you are seeing if you have drawn magnitude of hz uh, in uh, in reference to the z plane, right? So we have learned a few things about like poles and zeros, right? So we'll take a look. So hz I have shown you this equation previously. So it is like this. So in here, so take a look at the right hand side uh, derivation in there. What you can see is that is a multiplication. So multiplication, right? That symbol represent said my a 0, right? Then 1, right? Zk of z plane for which hzk equals 0, right? So I have told you 0 means a value where numerator becomes 0. So if the numerator is 0, hz will be 0. So z single zk is not a single, right? So we are substituting k equal 1 to n, capital N, right? So there will be n values of zk. So all of them are called zeros of hz, right? Which will make hzk. If you substitute z equal zk to hz will become 0, right? Means the set of pk values. So again, pk values, if pk is not just a single value, so pk will be like k equal 1 to n, right? Like p1, p2, p3, pm, likewise, right? Likewise. So therefore uh, in there uh, when uh, when you substitute z equal pk to hz, what will happen to hz is hz will be infinite. That's because when z is equal to pk, then denominator will become 0, right? So anything divided by 0, that will be infinite. When you substitute any value of the set of pk values to hz, it will become infinite. Therefore that is called pole. Okay, so what you can do is uh, you can draw pole zero plot, right? So pole zero plot means the plot of the zeros and the poles of hz in the z plane representing right? So that from that thing we can actually predict few things, right? So we'll see what we can predict from this pole zero plot. Okay, so you know how to find zeros and you know how to find poles, right? So then you should be able to draw poles and zeros. One thing you can tell from um, pole zero plot of HZ is the region of convergence outside the circle and extend to infinity, right? Rational HZ has ROC outside the outermost pole and the denominator greater than of numerator, right? So consider Hn equals 0 where 0, so so as an example here you can see Hz, right? Hz that is equal to 1 over 1 minus 1 over 2 into z to the power minus 1 plus 1 over 1 minus 2 into z to the power minus 1, right? So if we have found, right, hn you are getting as 1 over 2 to the power n plus 2 to the power n into un, right? So here the region of convergence, right, outside the circle and extend to infinity, right? So here what is the region of convergence in here? Magnitude of z larger than 2, right? So larger than 2 means that will extend to the infinity. Up to infinity it will extend, right? So starting from magnitude of z equal to, it will extend to infinity, right? So that is satisfied in here, right? Then hz has ROC outside the outermost pole and the denominator greater than of numerator, right? So that means hz has region of convergence outside the outermost pole and the denominator greater than the numerator. So that means that means uh, that means this will have, right, this will have, so let's say z equal, right, z to the power minus 1 equal z to the power minus 1 equal to, that means z equal half, right? Z equal half. So when z is equal to half, it is a pole. So what are the two poles of this thing? Yes, it is z equal, yes, z equal z equal half and z to the power minus 1 equal half, that means z equal 2, right? So the two poles are z equal half and z equal 2, right? So as ROC outside the outermost pole and the denominator greater than of numerator, right? That numerator denominator greater than numerator means there won't be a value. So that means that numerator cannot divide by the denominator. Okay, so that's what it says, right? So region of one outside the outermost pole. So what is the outermost pole that we have in here? It is z equal 2, z equal 2, and the region of convergence, that is magnitude of z larger than 2, right? So therefore this is coefficient. Any anything that will not uh, satisfy this, it will be non-quotient, right? So region of convergence should be outside of a circle, extend to infinity, so that is magnitude of z larger than 2, right? Then is outside the outermost pole, right? So magnitude of z larger than 2, and that is uh, that is outside the outermost pole. Outermost pole in here is z equal 2, right? And the denominator greater than the numerator, that means numerator cannot be divided by denominator, like if you can remember in in previous one, the long division, right? The region of, if the region of convergence includes the unit circle, what is the unit circle? Magnitude of z equal 1, then hz has poles inside the unit circle, then it is called zeros, right? Zeros 0.3, 0.6, right? And both P1 and P2, the magnitude is less than 1, which is 0.8. That means the poles are situated inside the unit circle, right? Inside the unit circle, right? So therefore uh, this will be stable. Again, the ROC will be magnitude of Z larger than larger than 0.8, right? So this is unstable. Here you can see poles are outside the unit circle. Okay, therefore it will be unstable. So stable and unstable means if you give an input to a stable system, the output will be limited, right? Limited. If you give input to an unstable system, output will be unlimited, which means unstable. So that is few things, right? So try to go over and over again with that thing, so then you will understand, right? So feedback block diagram is few, right? So here uh, consider something. So here when you have two systems, so one will have a set transform of the impulse response as H1Z, the other one will have it as H2Z, right? So like this. So here you can see you can represent it like this. So YZ, right? So YZ you can YZ of XZ. That HZ means the total total system Z total system transfer function, right? Total system transfer function, right? Here you can see uh, what you are getting is equal to uh, so here same thing. So right, H2 is into Y, H2 is H2 is into Y and multiply by H1, right? Starting from the right hand side, YZ into H2Z, you are getting here minus H2Z into YZ plus XZ, what you are getting is XZ minus H2Z into YZ, right? And that thing will be the output from there. So multiply that thing by H1Z, you are getting YZ, right? So simplify, then you will get the same thing. So remember when we have here H2Z, that is called a feedback block feedback part, right? H1 is the direct one, H2Z is the feedback. Okay. Uh, so in 1, right? 1. So therefore 104 is like H2 result. Okay. Z multiplied n minus 1 equal xn, right? So that is what this thing we can get by inverse Z transform. Actually not. Actually, you can see it here also clearly. Yn multiplied by Z to the power minus 1 means it is yn minus 1. Then here you are subtracting it with, sorry, multiplying it by 1 over 4. So 1 over 4 into yn minus 1, right? And that with xn, that is equal to yn. So if you put these things to the other side, you can get the same answer, right? Okay. So here by combining 1 over 4 and z to the power minus 1 and minus sign, and here this addition below you can see it is given as negative. So here, right? So two parts, right? Blocks. So combine. So what my advice in order to understand these block diagrams is, so write down for um, each and every place, write down its equation, right? Then come. So here I think what you understand is when you are multiplying, this is what happens. So in here first you will have your system number 1, second you will have the next system, right? So here again call this thing, right? HEG omega means the DTFT of HN, right? HZ is Z transform of HN, right? So here what you are getting is HEG here, right? How can we convert from one to the other? How can we convert from one to the other means how can you convert from DTFT to Z transform? Replace EG omega by Z. So how can we represent change from HZ to EG omega? Substitute Z equal EJ omega, right? So we can transfer function, right? So as I have shown you previously, you can actually draw the transfer function.